Okay, so here is where things get, in my opinion, a bit more interesting. We're going to start thinking about friction, which is nice because, as we know, the real world operates not frictionlessly. There's friction everywhere, and it wouldn't really make much sense to try and model reality if we were ignoring friction all the time. Um, so now we're going to start to get some understanding of how friction actually works and how we can model it mathematically. And fortunately, I would say it's quite simple. The equations sort of guiding how friction works are not too complicated, and hopefully they do make a sort of common sense. They should do. They align with what you experience in reality. But I do think it's important that before we launch into the maths of it first, we sort of just talk about um, how does friction work, and just remind ourselves is our understanding of friction in the real world. How does it tend to work? So let's just consider a few examples first before we actually get into the maths of it. So let's say, okay, so here's the ground. So let's say you're outside. In this case, the ground is, I don't know, it's just the pavement. And sitting on the pavement is some large box. Okay. Choose a box because square objects are easier to draw in this software. Okay, so there's my big box. Okay. And you want to move the box somewhere further along the pavement. So what do? You push the box, right? And consider for a moment, let me try and, this might seem a bit silly, but let me just try and draw a sort of pushing hand for a moment. Okay, not my best work, but this is what I'll come up with. So here is your hand, and obviously you'd use the flat of your palm to push a box, but let's just say for a moment you had a very strong finger, you're going to push it with your finger. So as your finger hasn't made contact with the box, there's currently no horizontal forces on the box, right? I mean, there's weight, there's normal reaction, but there's no horizontal forces. The box sits where it is. Now, imagine you're pushing your finger closer and closer to the box, and the moment it touches the box, okay, now picture it, it's quite a heavy box. Think about what happens in reality. The moment your finger hits the box, does the box start moving? And hopefully you sort of recognize that it won't. Not initially. You'll push it, your finger will be touching the box, your hand or your palm or whatever, you're pushing at the box, and you'll be pushing more and more and more, depending on how heavy it is. And eventually, with enough push, the box will start moving. And it'll almost feel like a release. Suddenly the box begins to edge its way along, and you keep pushing it and it starts to move. Okay, if it's a very light box, then it might feel like it moves straight away. If it's something very heavy, then it might take quite a bit of pushing before it eventually starts to move. And if it's something very, very, very heavy, it might never move. And what is preventing it from moving in the first place? It's the friction, right? I mean, I know we think, it's because the object's massive, but that's part of how friction works. So we'll see in a moment. There's sort of two components to friction. One of them being how massive the object is, in some sense, and the other being the nature of the surface that is involved. So let's say, for instance, imagine this same scenario, except I'm just going to swap out, and this is some very abstract drawing here, but that yellow line represents a road. So let's just change it to a blue line, this time representing ice, okay, which is the classic sort of, frictionless or close to frictionless surface that we use when we're sort of modeling physics. So now your object is the same object, the same box, but it's sitting on a lake of frozen ice, okay. And ice is slippery, and more technically we could say ice is a bit frictionless. I mean, it has a little bit of friction, but there's not much friction with ice. So it's quite slippery. So when you start pushing the box, I mean, obviously your feet might, give way below the lake. Let's say you're standing on the road and the box is on ice. Okay, so your feet are quite secure. You're on stable ground. You push this box on the ice, and what you should find is that it moves much more easily than before. Okay, so even though it's the same mass, same object, changing the surface it was on made it easier to push. Okay, if the box was smaller, it would be easier to push. If the box was bigger, and by bigger I mean heavier, it would be harder to push. If it's on a slippery surface, it's easier to push. If it's on a very rough surface with a lot of friction, it's harder to push to get it to initially start to move. So these are the two components that are going to describe friction mathematically. Okay, in some sense, it's something about the surfaces involved, and something about sort of related to the weight of the object. Okay, so that's the important thing we want to think about. So to summarize this then mathematically, I'm going to introduce something, I believe it's introducing you to the concept of a coefficient of friction. Okay, so this thing, coefficient of friction, this is just a number which tells us something about the surfaces involved, or the interaction between two surfaces. So for example, a box on a lake of ice, or you walking on a rough road, or a ball on an inclined plane, which is a rough inclined plane, or any two objects. So any two objects together, taken as a pair, they've got an associated coefficient of friction. Okay, and it has some value. And the symbol we use, instead of writing the words coefficient of friction each time, the symbol we use is the Greek lowercase letter mu. Okay, so pronounce mu like the word for the sound a cat makes, and you're going to write it like this. So I'll just write it a few times. There's mu. Okay, this is how I'm writing it on my page. It's kind of like writing a P, except instead of swirling around, you just end up writing a U instead. Okay, so that's mu. So mu is coefficient of friction, and it usually has a value. I say usually, it has a value, okay, greater than or equal to 0. Okay. If mu equals 0, this means the two surfaces are like 100% slippery. There's absolutely no friction between them. Okay, so it's a bit of an unrealistic scenario. It's like the perfect case. Okay, so mu equals 0 is completely frictionless. Okay, and as you increase mu, you're talking about the two surfaces having more and more and more friction, and there's no limit to how high mu can be. So it can go to 1,000,000. I mean, it could go very, very high. Usually it'll be some number between 0 and 1. Okay, usually. But technically it can be more than 1. I mean, as mu goes to infinity, we're basically saying, the objects are sort of stuck to each other. Right? So they can't ever slide past each other. It's almost like an infinite friction. You could think of it that way, right? So mu is in some way telling us this property between two objects. Really, mu equals 0 is the sort of key value. This second line I've written here, that's more of an abstract concept. Mu will never really go to infinity. Okay, so the main thing you really need to know at this stage isn't so much specific numbers, but you need to have a concept in your mind of what objects will have lower mu's and what pairs of objects will have higher mu's. So if I said to you, the coefficient of friction, the mu, between two ice cubes, compare that to the coefficient of friction between, a shoe on the road, right, on a gravel road. Even though you don't know what the coefficients of friction are, you don't know what the numbers are, it should be obvious to you quite clearly the two ice cubes have a lower coefficient of friction than my shoe on the road, sliding on the road. Okay, because one of them clearly in your mind you can imagine is a lot more slippery, the two ice cubes, and the other has a lot more friction involved, which is my shoe on the road. Okay, so that's mu. That's the first component. It's the properties of the surfaces. The other component, let's not quite go there yet, is related to the weight. So specifically, the reaction force of the surface on the object. Okay, so if I go back to say this diagram here, okay, let's bring that back here to our consideration of reaction force. There will be some reaction force. We don't know what it is at this point because it depends on the weight of the object, and we, that, as you know, we call R. Okay, this is the other thing that affects how much friction there is. The greater the reaction force, the more friction there will be, and the lower the reaction force, the lower the friction will be. In this case, of an object on a flat surface, reaction force is the same as weight, right? Only because it's a flat surface. It's not inclined. Okay. If I considered a slightly different scenario where it was an inclined surface, okay, then as you know, the reaction force and the weight are not necessarily the same, or they aren't the same in this case, right? Because you'll have your weight going down, that's your weight, but your reaction force is going to be this thing here, this component of the weight. Okay, that's the same thing as the reaction force. So that component there and that reaction force are equal because it's not going into the plane or out of the inclined plane. Okay, so if you know that reaction force of the surface on the object and you know mu, then these are the two things we need. These are going to tell us the friction, right? That's the two things we care about: reaction force and the mu. You'll usually be given the mu as a number, or if you're not, then you'll be given everything else and you'll be asked to find mu. Okay. Right, so let's actually see how these, what the formula is for friction. I haven't actually told you yet. How do you use mu and R to get the friction? Okay. Hopefully, though, you know what I'm talking about now when I say the mu and the reaction force. So, this is the formula. It's barely even a formula. It's simplicity in itself, but make sure you remember it. And it's this: the maximum friction, the most friction that a surface could possibly sort of enact on an object is mu times the reaction force of the surface on the object. So it's mu times R. Okay, and that is the formula you need to know. There's some distinction here between friction and maximum friction. Okay, and this is something that causes endless confusion, and it would be great if listening to my explanation now it just makes sense to you, and then you don't have to worry about it again. So I'm just going to take a moment to see if we can think about this for a second. So let's go back to the diagram here. Okay, and you've got your reaction force. Okay, and let's give some specific numbers now just to make it a little bit less vague. Let's say I'm going to say it's a 5 kilogram box. Okay, so you've got a reaction force of 5G, that's my R, and let's say the coefficient of friction between the box and this surface is 0.2, for example. Okay, what is F max? Should be quite simple. F max is equal to 5 times 0.2 times G. Oh, that works out nicely. That happens to be G, which is 9.8 in this case. All right. So in this case, F max is 9.8 newtons. Right. That's the maximum force of the friction. So here's what that means. In fact, let me describe it first, and then I'll just give you a few examples to consider. I'm not pushing the object at all. My hand's over here. What is the friction on the object? It's 0. There's no friction. Right? There's no friction at all. It's just sitting there. Now I'm going to put my finger here, and I'm going to push. I'm going to say I'm pushing that box with 3 newtons of force. Okay. What do we think the friction is on this object? Or better yet, let me ask this first. Is the object going to move? The answer is no. Okay. The reason is no is because when you push an object on a surface, the friction will push back if it can. And in this case, the most that the friction can push back is 9.8. It's the F max. However, I'm only pushing with 3. So the friction can totally match my force, right? So when I push with 3, you're going to get 3 newtons of friction pushing back, and the object is not going to move, right? Likewise, if I push it with 8 newtons, the friction is going to be pushing back with 8 newtons. Okay, it will match me. Now let's say I'm going to push it with 10 newtons. What's the friction going to do? Well, what it's going to do is it's going to just do its best. It's going to try as hard as it can to push back against my force of 10 newtons. And in this case, the best it can do is 9.8, because I've now exceeded the F max. I'm now pushing more than the maximum possible friction. So the friction will push back with 9.8, and now the object moves. And in fact, the resultant force you can work out, because the friction pushes back 9.8, I'm pushing with 10, so you're going to have 0.2 newtons to the left. So the object's going to start moving left. Okay? This is the really fundamental part of understanding how friction works. So I'll just say it one more time. Imagine you've got an object, you've got your finger, and you're going to start pushing it. The moment your finger makes contact, there's no friction. The moment you start pushing a little bit, the friction pushes back the same amount, and the object doesn't move. As you keep pushing harder and harder and harder, eventually the object will move. And the point at which that object starts moving, that's when your pushing force has gone greater than the F max, which is this maximum possible friction. The way we find this F max is by multiplying mu, the coefficient of friction, times the resultant force. Okay, I hope that makes sense. All right, it's really important. So don't ever think that F max means that's what the friction is. It's not always going to be that amount. Okay, that's the most it can ever possibly be. Cool, I hope that makes sense. So we've got 2 examples to work through. Let's look at the first one. We've got a mass of 8 kilograms. It's on a rough horizontal plane. We're going to see the word rough a lot more now because we're talking about friction. And the coefficient of friction between the mass and the plane is 0.5. Right, let's start drawing things. So, horizontal plane, that's nice. It's a mass of 8 kilograms. I'm going to do a box. So if it's 8 kilograms, we've therefore got, let's just start adding things as soon as we can. 8 kilograms means 8g weight, and because it's on flat ground, the normal's the same, the normal reaction. What else do we know? Mu is 0.5, that's the coefficient of friction for the box and the plane. What's the maximum, the magnitude of the maximum force P which acts on this mass without causing it to move? So it's really 2 questions in one. If the force P is horizontal, and if the force P acts at an angle 60 degrees above the horizontal. Okay, so it's 2 questions in one, really. Let's do part A. So let's say there's a horizontal force P. Right, yeah. So this horizontal force, let's say it's going like this. Okay, now when that horizontal force P is going to the right, then to the left we're going to have, actually let's just pick a different colour just to distinguish it a bit. To the left we're going to have friction. Okay, the friction always acts, I'm using F for friction, the friction is always going to act opposite to the direction you're pushing. Okay, that's a detail I maybe didn't mention before, but hopefully is intuitive. So what's going to be the maximum possible P without causing it to move? So just think about what's going on there again. We're saying there's a force P, it's getting bigger and bigger and bigger, and eventually the box will move. So what's the biggest possible value the P could be just before the box moves? It's going to be when P reaches the F max, right? When you exceed the F max, that's when you start moving. When you equal the F max, then you're just about to start moving, but you haven't quite yet. You're still stationary. So for part A, really, we're just being asked to say, well, P is going to be equal to F max, which in this case is going to be equal to mu times the reaction, which is 0.5 times 8g equals 4g equals 4 times 9.8. Can we do that in our heads, or are we lazy? 39.2. Cool, okay, so that's the first one. We've got 39.2, that is in fact the largest force that P could be without the box moving. So for example, if P was 39.3, the box would start accelerating to the right because it would have a resultant force going to the right. Okay, likewise P is 40, P is 41, and so on. Okay, the moment the P exceeds 39.2, remember the F is still going to be 39.2 because that's the maximum value it can be. Okay, right, all right, let's take a look at the part B then. So in this case, our P is going to be at an angle pointing up to the right, and specifically an angle of 60 degrees. Okay, so we've got 60 degrees here. So what I'm going to immediately do actually is then just split this into the respective components, horizontal and vertical. So here we'll have P cos 60, and here we'll have P sine 60. And in fact, let's immediately simplify those, because as we know, sine 60 is root 3 over 2, and cos 60 is a half. So we can just write here, that's the root 3 over 2 times P, and that's a half P. Okay, and this 8g over here, we can't assume this anymore. Let's get rid of that. It's not 8g now, and the reason it isn't is because before we argued that this was 8g because that has to be equal to the weight so that the force is balanced vertically. But now the problem is that this P force has a vertical component. Before it didn't. Before the P was just horizontal, there was no vertical component. Now P has a vertical component, which means that this reaction actually is not going to be as large as 8g. It'll be less than 8g. So specifically, if we write reaction there, we know that the reaction plus this root 3 over 2p, so that's that vertical component there, that's going to be equal and balance out the 8g. Okay, so we can see that the r is going to be a bit smaller than 8g in fact. What else do we know? So remember, we're trying to find the largest value for P such that the box doesn't move. So in other words, the horizontal component of P is going to be F max. Right? So not P is F max, the horizontal component is F max. The reason being the friction always acts opposite to the direction of motion. And even though we're pulling this thing, we're applying this force P diagonally here, the object is still going to be moving to the right. It's not coming off the surface. Okay, so let's write that down then. So we've got half p, so that's that bit there, that half p component. That has to be equal to f max, which as we know is equal to mu times r, which is just 0.5 r, half r. And therefore, I'll just write it up here, we've got a half p equals a half r. So really p equals r, doesn't it? Let's simplify that a bit. P is equal to r in that case, which is equal to, if we just rearrange this bit in our head slightly, r is going to be equal to 8g minus root 3 over 2p. So let's just do that here. 8g minus root 3 over 2p. And now it's just a case of solving this thing. So we've got p equals that. Let's remove this in between value actually. So we've just got p equals that. Solve for p. So that's 1 plus root 3 over 2p equals 8g. And therefore p is equal to 8g all divided by 1 plus root 3 over 2. Okay, put that into the calculator. That's 8 times 9.8 divided by 1 plus, I'm just going to use sine 60 actually instead of writing root 3 over 2 because that's faster. Right, we get 42.01 roughly speaking. Okay. Cool, and that's our value. That's the largest possible value for p. So if p was 42.02, the object's going to start moving to the right. The force is not strong enough. Okay, and remember in this case, that's not the f max because that's telling us the value of p. The f max is actually half of this, isn't it? It's about 21 because the f max is going to be the same as the maximum force P's component, which is horizontal, being equal to that friction. Okay, cool. Hopefully that made sense. I think then we've got one last example before I give you a few questions. Okay. In this case, it looks like we're going to be finding the coefficient of friction ourselves, actually. Okay, so a plane, inclined plane. Let's draw a nice big diagram. It's 20 degrees inclined. Box of 10 kilograms rests on it. There's my box. Picking some arbitrary colours. We've got 10g down, that's the weight. On a rough plane inclined 20 degrees above the horizontal. Okay, right, there's a key word here we need to pick up on for a moment. Limiting equilibrium. Okay, this is giving us even more information than just equilibrium. It's actually giving us extra information. So there's a difference between equilibrium and limiting equilibrium. Well, limiting equilibrium is more specific. So if I say something is in equilibrium, it just means that there's a net zero forces on it, or it's not accelerating. Okay, it could be moving technically, right? Remember, if you're in equilibrium, it doesn't mean you're not moving. It just means the forces are zero, or you're not accelerating. So equilibrium means forces are zero. Limiting equilibrium means forces are zero and the object is just about to start moving. It's not moving, but it's just about to. So kind of picture a scenario where, say, I've got, say, I don't know, I've got a plank of wood and I put a ball on it, or let's put something a bit more rough, you know, a small little box. You know, I put my pencil case on a plank of wood, and then I tilt the plank of wood. Now, as I tilt it, the pencil case is not moving; it's just sitting there. The friction keeps it in place. And at one very specific moment, at a very specific angle, it starts to slide. It starts to slide down the plank of wood. So at that exact moment where it's about to go from not moving to moving, that exact moment when it's about to make that transition, that is called a state of limiting equilibrium. It basically means this thing is just about to start moving, right? So what that means for this scenario is this box on the slope, it's just about to start moving, okay? Presumably down the slope, okay? Right, so let's take that into account. So what have we got in terms of forces? We've got 10G, and let's split that up already actually. So that's 20 degrees there. This is 10G cos 20. This one's 10G sine 20. And what else have we got? We've got the reaction force. Okay, and we actually know the reaction force must have... Oh, let's not jump ahead actually. Let's look at the other forces. What else have we got? Oh no, that's just about it, isn't it? Except then the friction. Right, remember the friction acts this way, F. And what we know is that because it's in limiting equilibrium, not only is there friction acting, but the friction is at its maximum. So that's why it's useful to know something's in limiting equilibrium, because what that really is code for is the friction is at the F max. So not only is this F, it's actually specifically F max. It's the maximum friction. Okay, cool. All right, let's then break a few things down. So the R should quite obviously be equal to 10G cos 20. So that balances out. So now we have R. Oops. Mu. Oh, we don't know mu. That's what we're trying to find, isn't it? Right. Okay, so it's in equilibrium, which means that this F max, although I've drawn it as a massive arrow, is actually equal in length to that little component there, the 10G sine 20, because the horizontal components have to be equal. So we've got F max is equal to 10G sine 20. Okay. And F max, as we know, that's the same thing as mu times R. So let's actually just replace F max there with mu times R. Okay. So then from that, I'm going to substitute this R 10G cos 20 into here. I'm going to get mu times 10G cos 20. Actually, let me just give myself a bit more space. Mu times 10G cos 20 is equal to 10G sine 20. What's nice about this is that's the same as 10G sine 20 divided by 10G cos 20, and quite obviously the 10G and the 10G's cancel, so I just have sine 20 over cos 20, which is what? Tan 20, and that's it. We've got it. For part A, mu equals tan 20, and if you wanted to know that as an actual value, which you probably should do, it's 0.364, roughly speaking. It's about 0.364. Okay. Now the reason this is quite interesting is because if you think about it, this object, this 10 kilogram object, it turns out the weight was irrelevant, right? Because the 10G ended up cancelling. So the only thing that actually mattered was the angle. The tan of the angle gave me the coefficient of friction. This is not some rule that you need to be using in other questions, okay? It's a very specific scenario. It's when it's in limiting equilibrium. But what it does tell you, if you're interested, is that if you wanted to know the coefficient of friction of an object, or of a pair of objects, a surface and something on that surface, just tilt the surface by an angle, and the moment it starts slipping, that angle, take tan of that angle, you've got the coefficient of friction, right? So, you know, if you were going to do that, I highly doubt you're going to do this, but if you wanted to, you could put your pencil case on a plank of wood, something similar, tilt it. Once the pencil case starts slipping, what is that angle? Do tan of the angle. There's your coefficient of friction between pencil case and plank of wood, or any other two objects that you might choose to use. Okay, it's quite an interesting little result. Okay, let's look at part B then. A horizontal force of magnitude p newtons is applied to the box. Given that the box remains in equilibrium, find the maximum possible value of p. Okay, this is getting a little tricky, and it's because it's trying to catch us out on something here. I think relating to the direction of the friction. Okay, so before in our part A example, we had the weight. There's then normal reaction, and then you've got some friction going on. The reason we drew friction that way, going up the slope, is because quite naturally, if you put an object on a slope, its inclination is to go down the slope because of gravity. The friction opposes that direction up the slope. However, now we're being told, let's get rid of friction for a moment because we need to decide where it's going to go. Now we're being told there's some horizontal force of magnitude p applied to the box. They're a bit vague about the direction it's acting in, but it is, in this case, going horizontally. Okay, so we've got some horizontal force p. Okay, and what this means is that, well, if I'm pushing this, if I want to find this maximum value of p, then that means what's actually going to happen is this p is getting bigger and bigger and bigger, and eventually the friction's actually going to be acting down the slope, right? And the reason for that is because the biggest possible value for p would be one where the box is just about to start going up the slope, right? Because I want to increase this p as much as I can. So really this friction force is now, in this case, going downwards. Okay, it's opposing the direction of the resultant, which is going upwards. It's still Fmax this time though, right? Because again, it's going to be a limiting equilibrium, because I want to know what's the maximum possible value of p such that the box remains in equilibrium. So now we're going to have to do some resolving of equations, right? Let's see what we get. So we're going to have to split up this p first. Let's do that. What's this angle here between the dash blue line and the solid blue line? Should be 20 degrees, right? Okay, so then here we've got p sine 20, and here we've got p cos 20. And let me just put the arrows on these just to make it clear. Okay, so it's in limiting equilibrium, right? We know that because we're looking for the maximum possible p. Let's do some resolving of forces. So going up the plane, let's do it formally. We've got p cos 20 going up. We've got, let's not lose sight of them, we've got 10g sine 20. That one's going down. And we've got our Fmax, right? Our frictional force is at a maximum and it's also going down. Okay. And that's all equal to 0. Because it's not moving. Okay, and then what about, sort of vertically, perpendicular to the slope? We've got R going up, we've got P sine 20 going down, and we've got 10G cos 20 going down. So let's deduct both of those, P sine 20 and 10G cos 20, and that's equal to 0. Okay, it's looking a bit complex. I believe at this stage the book starts actually just turning these coses and sines into numbers. I guess I'm kind of a fan of trying to get an exact answer, so I might just do that, but we'll still get the final number in the end. let's just think for a moment, this F max, what should that be? Well, remember F max is mu times R, so let's change F max to mu times R. We found the coefficient of friction in the previous section. What did we say it was? It was tan 20. So starting to look a little nasty, but you know, let's not get too upset by this. We've got tan 20 here. That's our mu times R, and that's equal to 0. Okay, so we've got two equations and two unknowns. Capital R, capital P are our two unknowns. This should be solvable. We should be able to find a value for P. Okay, let's give ourselves some space and see if we can do it. You can also give it a go yourself. Let's see how we get on. So let's see if we can fire through this. R must be equal to P sine 20 plus 10G cos 20. Let's then, I'll do a bit of copy paste. Let's take that equation there, replace the R, there it's gone, and I'm going to replace it with what we just came up with here. So forgive me for being a bit lazy and not writing it all out. So we've got that. Ooh, it's looking a bit nasty. All right, let's not give up. Let's not give up. I'm sort of pepped talking myself here a bit. I'm not going to give up. Let's try and do this properly. So we've got P cos 20 minus 10G sine 20 multiply out minus P sine 20 times tan 20 plus 10G, no, not plus, don't rush, minus 10G cos 20 tan 20 equals 0. Quick double check, does that make sense? Collecting up the P's, I've got P cos 20, so that's that one. I've also got a sine 20 tan 20. And the other stuff doesn't have P. Let's move it to the right hand side. So I've got minus 10G sine 20, move it to the right. I've got minus 10G cos 20 tan 20, move it to the right. Let's take the 10G out. So put all that in brackets and get rid of that one. Okay, right, now let's do some supreme copy and paste. P equals, therefore, that thing. Oh dear. Our numerator, that's a 10. All of that divided by, oh dear, all of that divided by this here. Beautiful. There we go. Final answer. Almost. Right. Okay. Now we just got to substitute that into our calculator. So if you had just converted this to numbers earlier on, totally fine. Just be careful with rounding errors. At least having done it this way, though, there hopefully won't be any rounding errors. So let's put that in the calculator. See what we get. Yes, it's right. We get 82.23, roughly speaking. Newtons, and that's our answer, the maximum possible value of P. Nicely done if you were able to follow that along. Cool, okay, so let's try some questions of our own then. We've got 4 questions total. The first one's a shorter one, and then the other 3 are slightly more in depth. Okay, so hopefully this one's not too bad. This is more just the basic concept. Question 3. Give it a go. Pause the video now. Okay, and let's look at the answer. So not limiting, presumably that then means the friction is not quite equal to F max. Okay, question 6. You've got an object going up the plane. So just a hint for this, remember, right here, this is a key sentence. The particle is on the point of slipping up the plane. So again, if you're on the point of slipping, then that means not only are you in equilibrium, but the friction is equal to F max. Okay, it's reached the maximum possible friction. So it's in a limiting equilibrium. And not only that, because it's on the point of slipping up, that means the friction is maximum, but the friction is acting down. Okay, so the friction is actually pushing it down the plane, and the ball is about to start moving up. Okay, so be really careful with how you label the friction. The friction should be going down the plane. Okay, so give that question a go. Pause the video now. Okay, and there's your answer. 0.6 is apparently good enough. Okay, question 8. Similarly, an object on a plane, you've got a mystery force acting on it now. And you're going to be having to look at finding coefficients of friction in this case. Okay, big diagram, please. Draw a nice big diagram. Find all the components of the relevant forces. A lot of this is all in the diagram. If you can draw the diagram accurately and you're not confused about where the forces are and which way they're acting, you're going to have a lot more luck with this. So try and draw the diagram as accurately as possible. Okay, when you're ready, pause the video now. Okay, and there is your answer. And final question about a small child sliding on a sledge on a slope for the years when it used to snow in England. So it's on the point of slipping, key sentence, sledge is on the point of slipping down the plane, therefore the friction must be acting upwards. And you've also got a string going on here with a tension as well. Okay, so again, it's all very related. They're all quite similar-ish questions, but with a few elements here and there changed. So in this case, you've got a string with a tension you've got to take into account. Okay. Cool. All right, give that question a go. Pause the video now. Okay, and there is your answer. Congratulations if you got it. T should be about 102 newtons.